Hello, my name is Anton Antonov. I am a co-founder of a company, Ascendo Data, in which I act as a senior applied mathematician. My talk is about exemplifying cultural differences between machine learning and statistics. The abstract which I have published when I submitted this talk like 3-4 months ago, it's not very actual, but I have made some updates. Before discussing what I'm going to present, I would like to say that I do have some background bias. My background is in large-scale air pollution simulations. I did study general algebra before that. In large-scale air pollution simulations, these are a lot of scientific subcultures, solving PDEs, ODEs, grid generation, computational fluid dynamics, large-scale linear algebra, also lots of programming. I do like operations research. I have worked on optimization problems for the industry. And so when it comes to statistics, for whatever reasons, I have been always kind of suspicious of statistics and statisticians. Very often, I don't see why the statistical language should be used. Ultimately, we use linear algebra and optimization. So this is not necessarily a good attitude. I just think it's a valid one. I can show you that with this attitude, I have actually resolved lots of problems, which actually statisticians, at least the ones I have met, have not been able to do. For whatever reasons, in the companies I work for, with lots of data scientists and engineers, I have been playing the statistician role. So, but this is not because I want to, it's just sometimes really, we need to utilize statistics. I do think that statisticians, the successful statisticians, are more likely to be the so-called timid professionals. You can see this book, which is referenced there. It's called Disciplined Minds. And the successful machine learning practitioners are more likely to be maverick. Feel free to disagree with everything I said so far. But to some extent, I'm exaggerating a little bit in order to make a point. This is not about statistics. This talk is not about statistics and data science. Data science is much more general. It's the overlap between machine learning and statistics. And in this particular case, in this particular scope of the talk, it's more about predictions and recommendations. And in general, we can see data science and machine learning as part of statistics. If you deal with data, you're doing statistics. Where we have seen this? Well, in spectral element and finite element methods, you kind of do the same thing you do in statistics. So you come up with a model, you solve some optimizational problem, which comes with whatever Hilbert spaces you have been utilizing. Then you verify the model. Very often these models of the PDEs are linear, and you have some basis functions and so forth. So similarly, this is something you do in statistics when you do, say, linear regression. Use the Gauss-Markov theorem, which guarantees you that you'll get unbiased estimate and so forth. So basically, you're solving an optimizational problem, which you then you need to verify in whatever ways is it valid. There's some analogy in music, but I don't know. Don't go for it. So when it comes to the difference between statisticians and machine learning practitioners, I would like to point to the Pareto law, which is also known as the 80-20 rules. 80-20 rule. Like 20% of the statisticians contribute 80%, make 80% of the contributions. Now, I suspect that in machine learning, it's like 15% of the machine learners contribute, 95% of the contributions in machine learning. But whatever. Basically, this talk is more about the long tail people in these fields, and a reference for the rest of us. So I'm going to move to these three machine learning protagonists. The simple nuclear physicist is a guy who actually very often is responsible for lots of data, and they just cannot throw it away. This lots of data has been produced with, say, millions of dollars of investments. So in general, physicists can become very good data scientists. The other protagonist is the common operations research analyst, who might be working in, say, cruise line or whatever. In this particular case, he's going to be working in a riverboat casino. And the standard machine learning engineer, which is kind of me, basically called data scientist very often. So the major ideological differences and methodological differences were listed here. And one of the things which it's kind of the lessons to be taught from doing machine learning when it compares to statistics is that there's a multiplicity of good models. And my first example, more detailed example, is going to be showing that. Also, very often it's hard to produce simple models which explain the situation. In a sense, you have good prediction, you have a complicated model, like something like neural networks, etc. So this is why there is no Occam razor. And high dimensionality very often is considered a curse. This is a very statistical way to treat things. In statistics, very often people try to reduce dimensionality, remove axes and dimensions, and so forth. This is not what machine learners do. Like if you take something like support vector machines, if anything, you're actually increasing the dimensions. You're actually embracing the dimensionality, the high dimensionality. I do actually think machine learners, they oversimplify things, and same as statisticians, very often they try to see without looking. And one of the things they do very often is to do simulations instead of models, which is great. Of course, you need to be careful. Mashing up of algorithms, again, could be good, could be also very bad. And the standard application is to do collaborative filtering. Basically, you are outsourcing or crowdsourcing intelligence. You're trying to see without looking. These are not necessarily bad per se, but they're not necessarily good either. So you need to be careful when you apply them. This is the overview of the examples I'm going to go through in this talk. Maybe the detailed examples, it seems I won't be able to go through all of them in detail, but I have made very detailed presentations outside in different web repositories, and there are links to it. The whole talk is saturated with links and references. If you use this notebook, these are the packages which are used in this notebook to do computations. The first example is the receiving operating characteristic example. If you haven't seen before what ROC is it's basically this type of plot in which we're looking at the dependency between the true positive and false positives. Now, this is our standard, our simple nuclear physicist is doing this. One of the reasons I'm using him here is because physicists, they're very accustomed to do phase space portraits and investigate stuff in phase spaces. Even if they don't know, this physicist, simple nuclear physicist, doesn't know about the ROC curve and plot, he can actually come up with it. It's common sense. It's very easy to define. So what he's doing, he has some data set, in this particular case, the Titanic data set. And he's basically making a bunch of, he knows that he uses some kind of library, like say Mathematica. He makes several classifiers. You can see these classifiers. And he makes an ensemble of them. And this ensemble of classifiers, produces this result, which is, which basically the classification ensembles. Basically, when you have like 6 or 7 classifiers, if you put a record to this set of classifiers, you can just use simple voting, or you can do some averaging of probabilities and see what exactly is which of the labels is being voted. So you can see here that if we change this threshold with this particular ensemble classifier is being changed or biased with the probabilities mean. Basically, this threshold, which is when do we accept survived, when I change the threshold, I get different performance. And you can see that actually I can get fairly good performance around here. So it's but again, this comes from the ensemble. One of the things which we can do is, I think this is evaluated. So you can see that with the single classifier, this is the classifier with support vector machine, this one here. I get this blue curve. And with the bootstrapping classifier, bootstrapping ensemble, I'm getting this red curve. It's like, I do have actually quite good performance. With some of the other classifiers, this can be even more exaggerated. We say, let's actually try, since this is, I did actually spend some time to do this as a live demonstration. So the bootstrapping here, it's basically resampling the data in some way. And you can see that I have actually taken a slightly smaller fraction than the full data. And so here I calculated the bootstraps. And so actually in this case, I didn't get better curve, which surprises me. But usually I do. And then again, if I rerun, and yeah, I mean, let me change here the seed random, I very likely, will produce better curve. Okay, well, I'm not. But this again, like with the bootstrapping, it's exactly manifesting what I was saying earlier, that we can actually produce better models using an ensemble, and there is no simple explanation for that. So one of the things, and what this is. If we ignore this picture, if we look at the previous one, it is actually interesting to note why is this actually, why I was getting with bootstrapping, why I was getting better results. And one of the reasons here is that I do actually have outliers in the data. And you can see with this example here that if I systematically remove females from the data set, like records corresponding to females, I'm kind of using increasingly smaller females, I'm actually kind of having very different performance. And so here you can see this is the 0 point, and if I have removed, like say, 15% of the females, I actually get somewhat better performance. This is actually, I'm going to move to the next example, which is done with statistics. This is actually can be explained with using that we're having outliers in the data. This, by the way, it's a very simple, the whole thing with ROC statistic. It's very simple math. If you look at this article here, everything here, it's like pre-high school math. It's all ratios and so forth. It's fairly straightforward. There's no hypothesis testing. There's no statistical fitting or anything like that. So this is one of the things which machine learners do. They actually can utilize very simple techniques to produce better results. All right, so with it's an interesting thing to compare this with linear regression. If I do this with linear regression, which is more like using this model, I mean, I don't get a good fit. Actually, this term here with the epsilons, they're supposed to be identically distributed, independent, identically distributed variables. You can see with this predicted versus residual that this is not the case. We actually see some patterns. This actually means that it's a terrible fit. But we have done it. We can actually investigate further. What is interesting here, let me see this. If we look at so-called Cook distances, this actually, they tell us that we have outliers. Usually, anything larger than the threshold computed in this way, it's something that has to be examined. And we can see that we do have actually a fair amount of outliers in the data. So again, this is the statistical approach when you do this is the major model, so to speak. In statistics, we do have a model. We do actually, statisticians, they do use the identically independent distributed variables as a tool fairly often. It's as important as, say, uniform convergence in calculus. It's used for almost any method to be derived. And when they try to apply a method or model, they basically, this is how they evaluate it. They actually want to see, after we have fitted everything, is this assumption valid? If it is valid, then our model has been valid. If it is not, then we need to do something else. Machine learners don't do that, but they actually say with these ROC characteristics, they actually can produce somewhat better results. I'm out of time, so I'm not going to discuss the progressive jackpot modeling much. What I'm going to show and maybe this is not a good idea. But basically, instead of using neat math for progressive jackpot modeling, we basically have a jackpot in some slot machine or lottery, which is accumulating part of the ticket. When you buy a $1 ticket, say 10% is being withheld for the jackpot, the rest goes for the organizers. So the variety of questions, how much of tickets need to be purchased within a month in order to the jackpot, say, not to be won more than twice in a year, and what is the probability to the jackpot to be won before it reaches $500,000, and so forth. So I mean, you can use this neat math perspective. With mathematics, actually, you can actually solve some recursive equations, use binomial distributions, and so forth. The thing is that it's better to do simulations, and one of the things is that it's like I use here Poisson process, but the thing is that the organizers, they might have some brilliant ideas which will change your neat math quite dramatically, or it's going to be impossible. Like they might say, look, after somebody wins the jackpot, we don't want to start from zero because nobody's going to play. So we want to actually also withhold some percent for a withheld pot, which is going to jumpstart, the jackpot thing after it is won. So what happens then in that case? And what happens if slot machines, they have very different performances when they're placed in different places in the casinos. So basically, you might have some kind of temporal and spatial variance of how many people play these machines, where and when, and so forth. With the simulation perspective, this all can be addressed, and this is discussed at length in this notebook. So this is another. I have only 7-8 minutes, so again, this detailed explanation, I'm not going to go through it, but what is happening here is that this is a typical, actually, example in which, so we have some distribution which we don't know. This is X, and we know that Y is some kind of noisy distribution. It's a normal distribution. We know the variance, and so after we have the mixture, which, actually, if I probably need to evaluate this because it can be more dramatic than what it is shown. After I have this mixture, it might happen that, wow, this is really not good. Right. That's a great suggestion. What I'm going to do is to look at this here. So basically, this is the mixture model. So basically, I mean, you can see that, what I'm saying is that I can come up with a procedure which this Gaussian noise model, I'm going to find a function which is going to be 0 on any variable that has Gaussian distribution. That's, for example, kurtosis. And it's going to be non-zero to anything else. And so in this way, I can formulate a optimizational method which is going to extract the Gaussian noise variables. This is described here. This, again, it's full detail. You can actually see. You can see how minimize is applied, how maximize is applied, and so forth. We do actually can reconstruct the PDF and the CDF in this way. And it is more or less what you expect. Or at least in this particular case, this was what the user here wanted to do. All right, so I'm going to need to select some example here. Very quickly with quantile regression, you basically fit a bunch of curves, not just one. Like this is the whole point, I would say. You can see, I'm sorry if it is at the bottom, too much of the bottom here, but with linear regression, you can just fit a curve which is in the middle of this original signal. With quantile regression, I can fit multiple curves at different quantiles, and so which I have selected. It's a very powerful method. You can reconstruct the distribution at any given time point here. You can reconstruct the distribution of what is happening. You can see that some of standard statistical assumptions, that the variance the variance is not changing in time. They don't hold for this series. Actually, if anything, you can see that like the variance is quite wildly varying. This is in Atlanta, Georgia, during the winter, and it's much more stable. The signal is much more predictable in the summer. So I do consider this to be part of data mining, not so much of a statistical method, because in a sense, this is just it's a certain optimizational method which you apply to kind of conditions about the points. I mean, you just want some points to be above and below. There is no device like, say, the Gauss-Markov theorem behind this. It's actually fairly data-driven, fairly straightforward in a sense to apply in not effective way. If you want to apply it in an effective way, yes, you need to do linear programming formulation and so forth. So what is interesting here, and this is another thing to discuss, is that if I look at the bands between, if I look at the bands made by these quantile curves, like this is my first band, my second, fourth, and so I have like 7 bands, I can actually see, use a sequence which corresponds to this time series. Basically, I'm looking where the time series is if a point is here, this is the second band. Then if the next one is here, it's the third band, and so forth. So I can actually form a sequence like this, and then I can apply sequence mining algorithms. So you can actually, if you have a collection of time series, if you do that, you actually can also look at the general distribution across the collection of the different states and apply information retrieval techniques and so forth, like use natural language processing type of techniques, Markov chains in this particular case. This here gives you conditional probabilities, say, from state 6 to stay in state 6. This tells me what the probability is 7% and so forth. This was a very interesting example, which I gave during lunchtime at the Stack Exchange table, so I'm going to skip it. And this was also a great example, which I really don't see how we can cover. I do actually want to discuss this. I already mentioned this, but so in statistics, very often we do that. I mean, we gather the data, transform it, clean it, normalize it. This is actually very important. Fairly often, machine learners don't do it, especially if you do crowdsourcing. And this was actually the crux of this algorithm here I wanted to show. When you use graph-based models, graph-based databases, you don't need to clean your data that much, not in the way statisticians do. You can actually just connect the data as is, from transactions or whatever, and produce relatively good results. Here there are several. In another presentation here at Wolfram conference 2-3 years ago, I actually did this breakdown of problems and algorithms for machine learning. So basically, if you want to explain what machine learners do, in some sense, it's much easier than probably. With statisticians, this is kind of like some sort of longhand type of write-up, but we do actually, in both cases, there are certain established models and ways to kind of methodologies and ways to approach real applications. So this is the attempt here to list that. So this example here from scratch, well, it's very interesting, but unfortunately, it's without pictures. And so as a summary, I do actually want to accentuate to this. This is more like a recapitulation example of, if I want to make some kind of anecdotal, memorable image of the difference between statistics and machine learning, I would say this is it. You can see the first one, which is made with singular value decomposition. I have made a classifier, which is recognizing 100 digits, 60,000 digits, 10,000 test digits, so forth. So you can see that this classifier has produced these basis factors when I use singular value decomposition or principal component analysis. I have the middle digit, which is in the top left, and then I have differences between that. So basically, with there's some neat kind of theoretically justified math to do this, and Yeah, I mean, it's a very statistical method. You basically start with a mean object from the set, and you kind of subtract from it, and you basically will be analyzing these error vectors. And you can see that they're actually kind of somewhat hard to explain. Now, in machine learning, the machine learning perspective for this is this second algorithm which I have applied. It's non-negative matrix factorization. And you can see that in this case, the bases, all of the bases found, they're interpretable. So these are all different types of fives which have been used in the data set. So in a sense, it's an when I want to have an unknown digit, I need to solve an optimizational problem, how I can best represent it with these known fives. And in my opinion, this is kind of a good recapitulation of the differences between machine learning and statistics. There are a fair amount of references, also links inside. I strongly suggest the first link of Box, which describes how Fisher has been doing statistics. It's very different, apparently, from what statisticians do now. And the Leo Brayman article, which I used already mentioned stuff. It's very useful to read more about this kind of differences. Thank you for your attention.